You've probably been asked this question an insane amount of times. If you were to have any superpower, what would it be? If you're an average person, your answer would be something along these lines. The ability to fly, invisibility, super strength, teleportation, the power to control elements such as wind, fire, earth, or water. But if you're different, you'd pick a superpower that gives you the ability to control objects with your mind. Telekinesis, or the ability to control objects with your mind, is derived from tele, meaning long distance, and kinesis, meaning motion. So, if you combine those two together and throw it in a pot to cook, you get Google's definition. The supposed ability to move objects at a distance by mental power or other non-physical means. In order to understand this, imagine you're Luke Skywalker using the Force. Or, if you don't know what I'm talking about, then imagine you're Neo from the Matrix, stopping bullets with the power of your mind alone. From helping people with minuscule tasks, such as picking up your laundry and putting it in the washing machine, to life-altering events, such as pushing away someone who's about to get hit by a car, the amount of potential telekinesis has to enhance and improve our everyday lives is just exponential. And what if I tell you that some form of it is already a reality? Crazy, right? Our brain is made up of 86 billion neurons. For context, that's roughly the amount of stars in the Milky Way galaxy. These neurons form complex pathways that allow us to perceive the world, make decisions, and execute actions. In the case of a neuron, the electrical signal travels down the length of the cell, from the dendrites, the receiving end, to the axon, the sending end, in a matter of milliseconds. Once it reaches the sending end, the action potential triggers the release of neurotransmitters, which then go on to activate the next neuron or target cell. With the power of brain-computer interfaces and electroencephalography, we measure these action potentials and encode them into a computer or any device in order to control them, such as prosthetic limbs, XR headsets, and exoskeletons. This all allows us to make telekinesis a reality. In today's video, I want to share with you a simple, quick, easy way to get started with brain-computer interfaces without any EEG reading headband. In order to follow along with this video, be sure to check out my article linked below, which goes over a detailed overview for each step. Follow the steps 1 to 4 on your own, because they are fairly straightforward and are easy to understand. This tutorial video has two components. The first, the problem statement. Here we'll go over the purpose behind our project. The second is a high-level overview of how the neural network works, because we're going to be creating one to solve the problem statement. Let's get started. Let's say we had a guy named Bob who graciously accepted our offer to run ethical tests on him if we treated him to McDonald's afterwards. We told him to sit in front of a screen that was playing a slideshow of a set of images. These images were actually just checkerboard patterns that we showed to both his left and right eye. We also played some tones in his left and right ears. The interval between each image in the slideshow was 750 milliseconds, and occasionally, a smiley face was presented at the center of the screen. After seeing the smiley face appear on the screen, Bob is to press a key with his right index finger as soon as possible after the appearance of the face. Our mission is to only use the EEG data feed provided to detect when Bob is shown the smiley face before he presses the key. This is going to be done so that we can observe his surprise or anticipation response. This is usually found in something called the P300 component. The P300 is basically a spike, or you could say a positive deflection, that shows up after 300 milliseconds of observing a rare stimulus. In this case, rare stimulus equals smiley face. Now that we've covered the purpose of this project, let's move on to how the code works. Okay, now we reached the tutorial stage. Congratulations for making it this far. please look over the article and follow steps 1 to 4 because that's the background basis that you need to actually understand this code. So the first thing we do is actually import all our packages that we got from step 3. Then we set this random seed, which is a random generator, to 100 so that we actually have some stability in our code. Then we initialize the parameters that we need for this code, which includes e.g. sample count, learning rate, sample length, number of classes, hidden 1, hidden 2, hidden 3, output, hidden 1, hidden 2, hidden 3, output, and number of classes are all part of this neural network. Then we actually create and define this neural network. We save it in something called tutorial model, and we graph these input layers, these hidden layers, and these output layers. And we have something called an activation. Now this activation is this threshold that you need to pass in order to move on to the next layer. And in the output layer, your final result should be a number either 1 or 0. 1 meaning that's a P300 component, meaning that the person like Bob has actually seen the smiley face, and 0 means that he has not. But a neural network means that you actually have to train it yourself. Like it actually understands its own code and it realizes, hey, this is where I went wrong. So here, the way that's doing this is by defining a loss function. And then after we do that, we actually define and train the network. And we have this loss data, which is an array. Then we type in a for loop for I in range and the parameters iterations, so the number of iterations that we have. We classify each one by accessing tutorial model and trained data. Then we find out how long our network was during the iterations. And then what we do is that we take those iterations and we make them zeros, meaning that we just say that these are not P300 components. That's what we do in the optimizer.0 graph. Then we teach the network how to do better next time. So we're saying that this is wrong, so you have to step over and need to do this differently so that the code actually becomes a 1 instead of a 0. And then we save that. So in order to test this out, we create a sample data, and in the sample data we create positive sample data sets, we create negative sample data sets, and we graph this to make it understand, which is like right here. So that this is just for our own personal view so we can actually understand it. I'll show it later on. Then we classify these positive data sets, we classify these negative data sets, and we print these results overall. And this is another scatter plot so that we can actually understand what we're talking about. Of course, I'll get to that later on. Then we retrieve the data from like the actual data set that we need to use. And what we have to do here is that we have to kind of pick and choose what channels we want to use. Because what happens is that there's a bunch of data in this M&E library that we installed. And we want to get that specific EEG and EOG data. The reason why we're not getting M&E data is because M&E is inaccessible for people like us modern day people. We don't have the technology or the size of a room or the physical capabilities to actually host an M&E device, even though it is more specified. So here we're basically just picking the data that you want. Then we're also picking it from here, and we're looking at different channels that we have in our brain, right? And we're seeing that channel 058 is actually the one that's highly correlated to the P300 component. So that's why we want to specifically access that one. So that's why we're like, plotting the image so we can actually understand where it is, and we're picking it here. And then we're basically gonna squeeze this data so that it can become like, more specified, and we can specify the outliers in the scenario. So the P300s have it like, we squeeze them into 9 samples. We squeeze the 208 non-P300 samples. Then we scale all this samples so that we can actually have more data to work with so that we can have a more accurate neural network. We also scale the non-P300 data. Then we prepare and train these tensors. And we specify the positive P300 training and test samples, and we specify the negative P300 training and test samples. Then we combine everything into their final structures, and we print the size of each of our data structures. And after this, we actually generate the training labels that we're going to use. And we're going to make sure we're starting from untrained every time. So we're going back, to that neural network in the start, and we're just loading it up. Then we're defining a learning function that needs to be reinitialized at every load. And then we're using our training procedure with the sample data over here. Then we're classifying our positive test data set and printing the results. And we're classifying our negative data set and printing the results. We basically have to just take this graph and we're gonna see that if the P300 component or this neural network actually works with our real EEG data. So if we actually run this code, we'll see that we get something along these lines. The first graph that we'll get is sample data. And the sample data set is the first thing that we did. We created that sample data set and we saw if the P300 brainwaves are actually present or not, and the negative P300 brainwaves are actually present or not. We plug this into our neural network, and we see that, hey, this actually works. Then what we did was we made it into a scatter plot. So in the scatter plot, it was just a more detailed version to see how the data points actually work. We made this into a heat chart. And then the heat chart, we see that the P300 component happens around this section. And if you look at the deflection, it happens around here. And if we zoom this out, we will see that the EEG 058 channel highly correlates to the actual P300 component. So that's why out of all these channels, 126 channels, we're picking the EEG 058 channel. And this can be further supported by this graph over here. This graph over here takes the P300 component and another component. If we look at the P300 component here, by the way, this is from channel 058, we see that we have a deflection around the 0.3 and 0.4 millisecond area. You see that deflection over here, and it goes back up. But if you look at another brainwave, just any other brainwave, you see the deflection is not present. This shows that this is a P300 component, and Bob has seen the smiley face. Last but not least, we're actually going to look at the neural network that we trained. We're going to see if the EEG data that we put in actually works or not. So this is all the properly classified P300 components that we have. And then this is all the negatively P300. Pretty good, right? All of them are classified properly, except that one black line. The black line is actually supposed to be a positive P300 component, but our neural network misclassified it. And there's a reason as to why this happened. This is because a regular neural network takes around 100 data points to make it really accurate. But with our situation here, we only had 9 data points because we compressed and scaled the neural network data points that we had for the P300 component. That's why there's a room for error here, and there's many outliers. So this is just one case. But if you can somehow add 100 new data points, this will be way more accurate. I'd say right now it's around 50% accurate. And there you have it, folks. A high-level tutorial to detect when a person sees a smiley face before they click the respective button. If you want a more detailed version of this tutorial, check out my article, which deep dives into the nitty-gritty of how this project works. Thank you, and have a good day.